Hello students, in this class we will study degeneracy in transportation problem. So by degeneracy we mean that our basic solution is not, our initial solution is not basic feasible, that is degenerate. This case arises when your number of occupied cells are less than m plus n minus 1, where m denotes the number of rows and denotes the number of columns, and m plus n minus 1 should be the number of occupied cells. So for example, I am taking this transportation problem here and obtaining the initial solution by Vogel's approximation method. Okay, now we will try to see whether there is degeneracy or not. Okay, so this is the problem, and A, B and C are availability centers, whereas X, Y, Z are demand centers. These are costs: 8, 7, 3, 3, 8, 9, 11, 3, 5. These are the costs. Now we have to obtain the initial solution. Yes, these were the availabilities: 60, 70, 80, 80, 80, 50. Okay, so we applied the Vogel's approximation method as was told to you earlier. So what we did, first of all, we find out the penalties, that is difference between the lowest and next lower costs. So 7 minus 3, 4, then 8 minus 3, 5, and 5 minus 3, 2. Row wise, similarly column wise, we can see 8 minus 3, 5, and then next 7 minus 3, 4, and this 5 minus 3, 2. Then what we do, we select the highest difference among these. So you can see it is 5 and 5. So you have a choice to choose any one. Okay, so if I choose this column, okay, column wise, okay, this maximum difference here. So in this particular column, the minimum cost is 3. So we will do the transportation or allocation in this cell now. So corresponding to this cell, 70 is available and 50 is required. So minimum of 70 and 50 is allocated over here as I told to you, and thus 20 is left. Okay, and I have crossed here, nothing is required now. So we will not compute further these differences along this column, or we will not consider this column for further computation of penalties. Then we are left only with two columns. Okay, and again we do the same procedure. We compute the differences, and then we select the higher difference and go in particular row or column, and then do the allocation. And after we have done this three times, we got this allocation or initial solution: 60, 20, 50, 80. We can see that m is 3, n is 3, so m plus n is 6, m plus n minus 1 means 5. There must be 5 occupied cells, but we can see here these are 4 only, indicates that there is degeneracy at the initial stage. Okay, so if there is degeneracy, there will be problem of cycling. The again and again we will reach at the same table, and we will never reach at the optimal solution. So what we do, so here I have written this number of occupied cells are 4, but therefore there is degeneracy in transportation problem at the initial stage. So what we do with that, whatever number of occupied cells are less, we add those much. Okay, we add zeros to those cells, or we add delta or epsilon, and when we say that delta tends to 0 or epsilon tends to 0, but it is also quite feasible or quite easy or quite valid that you can add 0 to any, allocate 0 to any empty cell in order to make the number of cells as m plus n minus 1. So I am putting this 0 over here inside the circle. Okay, you have a choice. You can put either in this empty cell or in this or in this, but we should keep in mind that we should allocate this 0 to that cell which makes maximum number of occupied cells either in the row or in the column. So if I am putting it here, so in this particular row there are maximum occupied cells. Similarly, I could put it here also, and in that case in this column there are maximum number of occupied cells. So with this, if I proceed, okay, I'm doing so. What happened now? I have removed the degeneracy by doing this. Okay, next step is just to go for optimality and compute UI, VJs, and so on. Okay, just see now here. This was the table, and 0 was allocated here. Now, if I take this u2 as 0, so this will help me to find out all this v1 v2 v3 at once by using these formulas like Cij is equal to ui plus vj. So this, with the help of this is this is c21, so u2 plus v1, and this is 3 is equal to u2 plus v1. U2 is 0, then v1 directly comes out to be 3. Similarly, we can find this with the help of this 8 and 9. So v1, v2, v3 are computed directly with the help of this. Now we need to find u1 and u3. So for finding this u3, we can use this. Okay, and this is occupied cell, and here v2 is this. So 3 is equal to 8 plus u3. So from this we get u3 is equal to minus 5. Similarly, we find with the help of this, we find u1 is equal to minus 6. I have done some computations here, you can see, and this will help you to learn all this. Now next step is to find out DIJs for the empty cells. This cell, this cell, this cell, and this cell. So for empty cells, okay, this D11, D12, D31, D33. So the formula was Cij minus Ui plus Vj. So we did that. You can see in those cells that D11, C11 was 8 and U1 was this minus 6 and V1 was 3. And likewise we did this, all these computations, we found that all these are positive. It means that Dij values are positive for empty cells, therefore the solution is optimal, and hence the optimal solution. Whatever we obtained, that is optimal now. X1 360, X2 150, X2 0 means nothing should be allocated to this, X2 320 and X3 280, and minimize yet that will come out to be 750 if we multiply these with corresponding costs in the cells. Okay, this is how we handle the degeneracy at the initial stage. And now I am taking up another example where we can have degeneracy during the selection stage. So yes, you can see this is the table. This is the transportation table. These are the costs. It is cost structure, and these are availabilities, and these are demands. Okay. Now, initial solution by northwest corner rule, very simpler one. We start with the northwest corner. Okay, select that cell, then allocate minimum of availability and demand. So 40 and 30, minimum of 30. Okay, so everything is finished over here. 10 left over here. Then we go to the next cell in the same row, and again we find out minimum of those 10 and 30. 10 minimum be located here. Then everything is finished here, and here again we did this, some 20 units are left over here. Then we move down straight Okay, and we take the minimum of 30 and 20, that is 20 over here, and then all this supply demand is finished. Then we move directly to the next column, and again we do the same procedure, and okay, and same way we proceed, and we get this one. So this is 1 2 3 4 5 6 7 8, and these are 5 plus 4 9, 9 minus 1 8. So number of occupied cells are m plus n minus 1. Therefore this initial solution is basic feasible. Now during some intermediate stage we get, okay, we what we do, we find out ui and vj's, and then we do this, we compute dij's for empty cells, and we proceed on until the solution is optimal. And during some intermediate stage we find this table here like this: 1 2 3 4 5 6 7. So 7 occupied cells, not 8. Okay, and this is, there is nothing here, it is empty. Okay, so now in this case we need to put 0 somewhere, because 1 is less, 1 occupied cell is less, so we need to put 1 0. Had there been 2 occupied cells less, okay, then we would have put 2 zeros in any 2 empty cells, but in this case only one cell is empty, so we will put 1 0. So I can put here also, I can put anywhere, but if I put here I get 3 filled cells in this column, and that will help us to find out this uij and vj values. So here m plus n minus 7, but it should be hidden solution is degenerate, there is degeneracy, and we move on. So as told, I can put 0 here. Okay, and then now the number of occupied cells are again 8, and we can proceed to find out ui's and vj's corresponding to these rows and columns, and then we move towards optimal solution. So this is how we handle the degeneracy in transportation problem. Thank you so much.